Hi, everyone. Okay, very good. I'm here. Let's put this up. Okay, we're good. Great. Okay, well, good to see everyone again. I want to make it so that I'm in gallery view, just so I can see everyone here. How does this work? Perfect. Now I can see everyone. Okay, right. As some of you know, my life has gone haywire after releasing this Novid app. Sorry about that. We have lots of things going on right now because we're trying to stop COVID-19. But anyway, it's good to see everyone. We can still talk about some math. Math is always interesting. And I want to continue from where we were talking last time. We were talking about the saturation number. So saturation number, as we remember, what was the definition? Saturation number was the minimum, sat and h. That was the minimum number of edges in any n vertex graph, such that what we'll say is that it has no h, and adding any other edge makes a copy of h. Adding any edge makes an h. Okay, and what we saw is we saw that there were some examples of these saturated graphs. You could, for example, if you want to talk about saturation number of n comma kt, we saw some examples which were, here are kt saturated graphs. The idea was you take a kt minus 2, and then you kind of connect that to every other possible vertex. And I drew it this way. I drew it as a kt minus 2, and all the other vertices made an independent set. And we connect everything across like this. Just adjusting the volume. Okay, we connected everything across like this. Okay, and how many edges did this have? Last time the formula I gave for edges, let us see that if I have n vertices, the number of edges was linear in n, in the sense that it was roughly like of order t times n, because you would have t vertices here, about n minus t vertices, which is about n vertices there, and t times n in total. We think of everything in terms of n being very big and t being constant. Although actually in this case, we're not proving any asymptotic results, we're proving exact results. So in this particular case, we got an exact answer. But now I'm going to write the exact answer a different way. The other way I'm going to write the exact answer is as a difference. Actually, you can write this as n choose 2 minus something. So this has exactly n choose 2 minus, it's n minus t minus 2, which is n minus t plus 2, choose 2 edges. And why is that? That's just because I have a complete graph minus another complete graph. Okay, so now there's a theorem. The theorem is, let me make sure I have the names right. I want to say Erdős Heino Moon, but where did I put that? For me, somehow names I don't always have right, which is why that's frustrating. I left it somewhere else. Okay, so I will not write it on the slide, but I believe this is Erdős Heino Moon. This is a theorem from like the 1960s. And the only reason is I don't want to record on the slide something, record on the screen something written down, which is a not perfect attribution. But this is from around 1960s. And what we have here is that the theorem is that this is actually the minimum. So let's say every saturated graph, every H saturated graph, has at least this many edges. And this many is that many, the formula that we wrote. Okay, so now we need to prove something like this. If you look at this, how to prove it, you might try, not H saturated. I have a KT here. Every KT saturated graph. Every KT saturated graph has this many edges. Liam, you have a question. Just a second. I want to see if my audio here is on the mute setting. No, it's not. I should be able to hear you. Okay, I'll crank it up. Liam? Uh-oh. Maybe it is my fault. Let me see. Are other people able to hear him? HD audio. That should work. No. Sorry, 1 second. Oh, switch to the speakers. Let's do that. Trying this. Just a second. Let me make sure I got my audio settings straight. Oh, somebody said something in the chat. You can hear him perfect. So if you guys can hear him, then it's because I was doing something with the speakers before. Select the speaker. We will use the main speaker. Hopefully that works. And microphone array. Yeah, I want to use that. Let's see. So these things should work. Let me do a test speaker and microphone. Yes, I hear that. Hello, let me test the audio. That works. Okay, so in that case, we're both good. We're here. Okay, so in that case, could you say that again, please, Liam? Oh, no.
No, I was just.
Good. Yeah, I see.
Like, I was just checking because it didn't work for H, and then I was wondering if you could do it the other way around, switch the inequality and view it like upper bound, because every H is a subgraph of some KT.
Okay, so you want to think about it as, you want to flip the inequality around as an upper bound. So first of all, yes, so you're right, the H was, I shouldn't have written H, I should have written KT. And the next question is, can we do some kind of an upper bound, right? So what you're sort of saying is, H, not what sort of saying, you were saying H is a subgraph of KT if H has T vertices. So could you, for example, just use some kind of monotonicity, saying that somehow if I know the saturation number of KT, I can use the saturation number of KT to bound the saturation number of H. That's a question. So before I do this theorem, let's put down this very natural question. If H has T vertices, well then certainly H is a subgraph of KT. So then the question is, so compare saturation numbers of N and H and saturation number of N and KT. That's a question mark. Is this possible? What do people think? So what would be involved here? If we want to compare these two saturation numbers, we're saying something like, if you want to compare them, you're basically saying that if I already got the minimum number of edges that I could have in like one of these saturated graphs, what does that have to say with another one? Does anyone have an inequality you want to point out, or some observation about this? So that's also a good question because it helps us get familiar with the concept. Anthony. Okay, so you're saying like, suppose I've got a graph which is saturated for KT, right? And okay, so let's see where we're trying to go here. There's a claim. Let's look at the claim. The claim is that the saturation number of H is less than or equal to the saturation number. Let's put a claim with a question mark. Saturation number of N and KT, right? And the proof of this claim, why? Well, these saturation numbers are minimums, right? So what you're doing is consider a graph that is KT saturated. Well, not just a graph that's KT saturated, the minimum one, like the one with the fewest number of edges. So consider a graph that is KT saturated with minimum number of edges. And then what you want to show is this is also H saturated. If you could show that it's also H saturated, because I already have something with the minimum number of edges, that means that this graph is a candidate for the sat and H. And remember, sat and H is the minimum of stuff. So if this is a candidate, then the minimum of stuff would be even smaller. So that would be the thought. But now let's double check this. Show that it is also H saturated. What does H saturated mean? H saturated means it does not have an H. Well, that's true. That's okay. So there is no H because there is no KT. That's good. But the next question is, why is it true that adding any edge would make an H? Actually, that's not true. And it's not your fault. Actually, this is one of these things where you think about and you say, well, surely it's going to be monotonic. But it's not. So the problem here is that we actually don't know immediately that adding any edge makes an H. We only know that adding any edge makes a KT. So now the problem is that somehow, but don't know adding any, that's supposed to say any, adding any edge makes an H, only KT. And it's because of this that this question is hard to study. So, by the way, the reason I wrote all this down and why I asked you guys is because even for me, when I look at this, it takes me a while to parse the definition. So I felt if we all parse it together, then we'll make sure we all understand why this is a hard thing to analyze. Because it's not monotonic. Unlike the Turan number was obvious. Turan number just said the maximum number of edges with no something. Oh, well, of course, that's only one of these, like, does it contain the thing or not? In saturation number, there's both the containing the thing and also the somehow the ability for it to get the thing as soon as you add one more edge. So it's very annoying. It's got two sides. And I'm trying to use that to just emphasize that this is hard. And so somehow, the fact that there is a result like this is interesting. That somehow you can analyze a situation where you have sort of two things you need to worry about at the same time. Bryce is asking a question. Okay, so thanks for asking that question. You're saying that, wait a second. So if I know that adding any edge will give me a KT, wait a second. That's true. Adding any edge makes you a KT. Wait a second. So now I kind of like this, but the reason why, so maybe I have it wrong. Just a second. So adding any edge. Oh, that's where it breaks. Sorry. Yes. Yes. Thank you. Okay, so I got it backwards. Okay, thank you, Ariel, for pointing this out. Right, because you see, I knew that this was not supposed to work, except the one that I highlighted is not the right reason why it breaks. So, okay, first of all, yes. Yeah, all of these things about the containment are very easy to get backwards. So okay. So you do know that adding any edge. Here, I'll erase the don't. That's okay. So you do know that making this because it makes a KT. So that's okay. So that makes the KT. You will make a KT, but there, unfortunately, so that one's a yes, and the first one is a no. And the reason it's the first one is a no is because we don't know that it has no H. We only know it has no KT. Thank you. Thank you for saving it. Okay. Because I was like, this thing is not supposed to work. Okay. Good. Now is everyone, including me, on board with what the definition of saturation number is? Hopefully. So now let's think about how we can analyze this thing. We'll go back to the problem, and we go back to this statement where there's this picture. And then the question becomes, what can we do? So we need to now know about somehow saying that I always will have at least this many edges if I'm KT saturated. But as you know, I promised you that this was going to be an application of KL systems. I mean, we did some KL system, Bolobash theorem, where we somehow showed that the KL system maximum size was K plus L, choose K. And if you remember, KL system was we need to have set and other set. They are disjoint sets, so pairs of disjoint sets. Lots of pairs of disjoint sets, but somehow they intersect with each other when they're not the same in the same pair. And remember what that bound looked like. That bound looked like K plus L, choose K. If we want to use that bound, it doesn't look very convenient here because I have something minus something. Also, that was an upper bound, and this is a lower bound. I'm giving a ton of hints. Can anyone suggest what we might want to do? And I don't expect you to already know what to do. It's like, how could I make a KL system and an upper bound out of this? Is there anything in the numerics of what we see that make you indicate that maybe my KL system should have a K equals something or an L equals something, and there is some hope of seeing a bound of the form something plus something choose something? The hint is this is the wrong direction. Anthony. Oh, okay. I thought because I think I saw your microphone off, so I just assumed it was you. Okay. Anyone else? I actually do want to give you guys the chance to try this. This is something which, with that hint I gave you, is pretty useful. Philip. Oh, Aditya. T plus 2 choose 2? Say again? Yes. This one.
Should we treat n minus t as a k?
Yeah. Let's try n minus t as k and 2 as l, and then there's this 2. And so we are going to make a KL system out of this complement. So what we should do is, let's not talk about at least how many edges. How about talk about at least how many non-edges? Does that make sense? So I'm just motivating how, as soon as somebody tells you there's a KL system proof of this, then you see, based on the number, it should be k is n plus 2, k is n minus t, l is 2, and we should be saying the number of non-edges is at most something. So this is suggesting that for every non-edge, we make an A and a B. Do you see where this is going? Let's try it. So what we're going to do is let's prove that any KT saturated graph has at most n minus t plus 2 choose 2 non-edges. And the way you do that is we'll create a KL system. With k is equal to n minus t and l is equal to 2. And if I want to make a bound on this, which is going to be the bound on the non-edges, I should make, for every non-edge, I should make an A and a B. Okay? So for each non-edge, define, I won't do the indices. I'll just say A equals something and B equals something. A has to be a set of size n minus t. B has to be a set of size 2. I think that B is the easier set to define. I am pretty sure you guys all know what we would put for B, because we're bounding the number of non-edges. For each non-edge, that should be the 2 vertices, which are the endpoints of that edge. So B is the endpoints of the non-edge. Okay, now the deep question is, what's A? What could be n minus t? If I have this non-edge it's a KT saturated graph, there's a non-edge. So this is a non-edge. How do I illustrate non-edge? I guess I'll do something like this. That's a non-edge. And where could I get a n minus t vertices? Philip?
Everything that isn't in the KT created.
Yes. So if I added that non-edge, this is the KT that would be created. I'm just going to write KT would. I don't have enough space. But that's the KT that would be created. So let's let A be... Oh, by the way, there could be more than one KT that's created. Just pick one of them, okay? Like when you go and add an edge, when you make a non-edge into an edge, you could have made lots and lots of different KTs. Just pick any one. Pick one, stick with it. And once we stick with it, then what we do for A is the vertices not in the KT we picked. Okay, and it's not the KT, it's a would have created KT. So then we already automatically, by the way, we automatically get the disjoint, right? A and B are disjoint. That's beautiful. A and B are disjoint because obviously the edge is inside and the A is outside. So the only thing I need to check is what happens with two different AB pairs. So I just need to check. A situation where I have two different non-edges, right? I don't need to worry about what order, like whether it was AI where I is smaller than J or AI where I is bigger than J. I just have two of these different non-edges. So here's one non-edge. I'll do the purple for that, pinkish purple for that, and I'll use yellow for the other. There's another non-edge. At the beginning, I'm going to draw these two non-edges to use completely different vertices. We always have to think about how the proof extends if they are the same vertices. So I've got these two different non-edges. Now I need to draw the KTs. There's an important observation. As I draw these KTs, it is actually possible that one of the KTs uses one of the vertices. I mean, that's okay. You could have that one yellow vertex is in that KT corresponding to the pinkish purplish color. But the other one could also be like off on its own. So these are the two KTs. So now what do I need to check? I need to check that the A intersects the B. And because of symmetry, I can just go and say, well, let's just have the A for the A for the pinkish purple thing and the B for the yellow thing. So the A for the pinkish purple thing is everything outside. Oops. Everything outside. This part is the A. And the B for the yellow thing is actually just these two vertices. Okay. And why do A and B have to intersect? It's nice. The reason why A and B have to intersect is because I'm not allowed to have both of the vertices of this yellow thing both be inside the pinkish purple thing. Why? Because the pinkish purple thing is a KT except for that one edge. Did that make sense to people? Inside this purple thing, it's actually a complete graph except for that one particular edge. Therefore, because it's a complete graph except for that one particular edge, there's no way that both of these vertices are inside it, or else I would have two missing edges. And this argument that I just wrote also works if these two vertices happen to overlap in one vertex over there. Because ultimately, even if it overlaps in one vertex over there, well, one vertex would be inside and the other one would be outside, sort of like this. The bottom line is that this pink circle, or this pink region, is supposed to be a KT except for only one edge. And so, there's no room for the two endpoints of the other missing edge to both be inside. That's it. So that was what I just talked through. And so what this shows is that A and B intersect for different non-edges. So that's it. Actually, this is amazing. This is just not fair, actually. When I look at this thing, it's like, how in the world is this proof allowed to be so slick? Right? What is inside the proof? We're done. We just simply said for every non-edge, you let A be the things outside the KT you make, let B be the two endpoints of the non-edge. It's a KL system where K equals n minus T, L equals 2. Since it's a KL system, boom, the maximum number of them is n minus T plus 2, choose 2, which is up there. We're over. That's it. And that's the proof of the saturation number. So this is also not fair because all of the other problems about saturation number where it's not KT are not like this. In fact, some of these are extremely hard. If you have more questions, you should go and watch Deb Sumia's thesis defense, which at some point we should schedule. I think it's actually this month. Well, it has to be this month, but it's going to be somewhere towards the end of this month. If you're curious about hearing more about this topic, the funny thing is now it's going to be on Zoom too. So if you are friends with Deb Sumia, you can go and ask him. I'm sure he'd be happy to have people cheering on. Actually, speaking of these PhD thesis defenses, normally you are allowed, if you're curious, you're allowed to go and watch any of them. I don't know who else is defending this particular season, but if you're curious at all about what extremal combinatorics looks like or graduate level combinatorics looks like, I do encourage you, especially if you're a PhD student, to go and watch other people's PhD thesis defense, because then you can see what kind of problems people eventually do while they're studying. So yes, Deb Sumia's is coming soon, and I finally got a chance to glance over his thesis. So great. We have all of this. And that finishes this particular saturation number. Are there any questions about saturation? No? Okay. It's a beautiful topic. So if you're interested at all, I recommend, especially talk to him before he leaves. There are lots of interesting questions in this area. In that case, let me roll on to the next topic. Just checking on the time. Very good. So the next topic I want to talk about is, it's also about some type of intersections, but it's going to be a much, much simpler statement to begin with. And the much simpler statement is just, how big can an intersecting family be? So let's define an intersecting family of sets. A set family is intersecting if every pair of sets has non-empty intersection. Okay. So something that needs to be very, very careful here. It says every pair has non-empty intersection. That does not immediately imply that they have a common intersection. So that's the first thing whenever you look at these kinds of statements. The important note. it could be something that looks like this. Here I'll show you an intersecting family of 3 sets. And so these are 3 sets, and every pair has a common intersection. But it is not true that all of them have one intersection. So that's why we say pairwise intersecting as opposed to intersecting. Okay, so then the first natural question, if you're doing extremal combinatorics, is what is the maximum size? Maximum size meaning how many sets. It's not how big the sets are, but the maximum size of an intersecting set family if there are n elements. Well, actually, hang on a second. Let me write it in a more clear language. Maximum size of an intersecting set family where each set is a subset of square bracket n. Each is a subset of square bracket n. So now I'm being very clear. I'm saying somehow all of the sets are subsets of 1, 2, 3 up to n. And how big of an intersecting family can we get? This is the easy question. Anyone have observation of what you can do? Some way to make a very easy, very, very large intersecting family? Yes, Faye. Yes, every set containing the element 1. Take every set containing the element 1. And if I do this, I will get 2 to the power n minus 1 of them. And now this one is very easy to prove that it's the best possible. Does anyone know how to prove that you can't have any more than this? Yeah, okay, Faye's doing this. It's like the complement, right? You take the set and its complement. So, okay, and also, it's best possible I'll write not by, but since if I have an A and an A complement, these, somehow since these, you can only take one. So this is not perfect English, but I'll just write a colon, since these two can only take one. Okay, that's nice. Liam has a question. Liam, did you have a question? I thought I saw a hand. Maybe not. Anthony has a question. Oh, okay. Thanks for asking. What do I mean by A and A complement can only take one? What I mean is that for every subset of the n numbers, if I look at the complement of that subset, I cannot have both. Great. Oh, thanks, Liam. But we're just not going to get both A and A complement in the intersecting family because A and A complement don't intersect. So that's just an observation that you can take all of your sets, break them apart into something and its complement. From each such pair, if you want an intersecting family, you can only take one of them because they don't intersect. So that's all there is. Okay, here's another question. What else can you do? Are there other constructions? Are there other ways to make these? You know, like this is the most. 2 to the power n minus 1 is the most. Are there other ways to make intersecting families? So, I mean, we have a bound. The bound is 2 to the n minus 1. What are the examples? Is that the only example? Philip.
All sets of size k for any k strictly larger than n over 2.
Oh, so there's another one. Or all sets of size, we'll just say, wait, do you mean equal to k? Oh, okay, wait a second. I'm trying to think. If it's only equal to k, is that big enough to get through your 2 to the n minus 1? I don't think it is. Right? So I'm going to say that my question is, can we find anything else which is exactly 2 to the power n minus 1? At first I thought, oh, you were just saying all the sets of size which are bigger than half. But that wouldn't... It should work as long as n is even? So just a second. Are you saying all sets of size which are strictly bigger than n over 2? I think that's what you mean. Oh, yeah, that is what you mean. Yeah, it's not all sets of size equal to k. You want to say all sets of size strictly bigger than n over 2. And if you have all sets of size strictly bigger than n over 2, then certainly they're going to intersect because there's pigeonhole principle, not enough space, right? And in particular, you said that will work on a certain parity. So for example, if n equals, n has to be odd, I think, in this case. Is that right? Because I need to do with the ceiling. The ceiling of n over 2 has to be has to be a batch of sets, which is the same size as the batch of sets floor n over 2. So this works if n is odd. So we have this other possibility. Are there other possibilities? Oh, okay. So what you're saying is if n is even, then from every a and a complement, for n even, each of a complement, just pick one. So now that's a mess. Now there's like all of these different possibilities that I could take, right? Here I can have, what is this like? Thank you. Right. So you always will take the larger one. Thank you. Okay, I see. So let me not say or. It's just like, this or is actually an and. And for n which is even, each of a complement just pick one when the size of a equals to n over 2. That's the right way to write this. When the size of a equals n over 2. Okay. What I'm trying to convince you of is that somehow there's a lot of structures. And these lot of structures, I guess we could characterize them, we could try to characterize them if we want, but it will be a little bit messy. There will be lots of different possibilities. Yes, so there'll be a lot of different possibilities, which is unfortunate. Okay, but now the bound though is nice. The bound is nice. It's 2 to the power n minus 1. The next question is, what can we do to ask other versions of this problem? So for example, up here, what I drew is I drew a case where all of the sets were the same size. So here I drew a situation where all the sets were of size 2. Another natural thing to ask is, suppose I want to find the size of the largest intersecting family of subsets of 1, 2, 3 up to n, but here I now want to force that every set has size exactly equal to k. So I now have two parameters. And next question is for fixed n and k, for fixed n and k, what I want to know is what's the size of the maximum size, let's say not size, let's say max size of an intersecting family of sets of size k from square bracket n. So that's what we're interested in asking this time. Okay, does anyone have any ideas here? We don't have to have the best answer yet. I'm just looking for an answer. Anthony, I see. Okay, one way is to take all sets containing just the number 1. And when we say all sets containing number 1, remember that there are sets of size k now. I'm not going to do k equals 0. That's just kind of dumb. But if they're all sets of size k, then the number of ways I can do this is n minus 1 choose k minus 1. And the reason for n minus 1 choose k minus 1 is because, out of the n minus 1 other stuff, I can choose k minus 1 of them and then stick the 1 on. That's one way. Does anyone have any other constructions? By the way, I already pointed out, okay, I said k is not interesting. Sorry, I said k equals 0 is not interesting. There could be something else you might want to do, and the answer might even depend on how k and n compare. Philip.
If k is at least n over 2, you can just take all sets of size k.
You want to say if k is at least n over 2, do you want at least or bigger? I think you want strictly bigger right now. Take all sets of size k. Okay? And what this gets is this gets you, it gets you n choose k, which is in fact always bigger than n choose k, n minus 1 choose k minus 1 by this Pascal triangle type identity, right? With Pascal's triangle, n minus 1 choose k minus 1 plus n minus 1 choose k equals n choose k. So this is in fact bigger. But that only works when k is bigger than n over 2. Okay. Is there anything else that we can do? In fact, it's related to what we did, these three things that came up just now. We have not exhausted all three things. So we did the first line, we did the second line, and I guess since you already said it, Tingwei says you can also do the third line, by the way, because if I have all the sets of size, if n happens to be even, if I'm so lucky to have n even, then I could also actually just go and take every a and a complement, where a has set the size exactly n over 2, and just pick any one. So there's also the third one. If k is exactly equal to n over 2, that, by the way, forces n to be even, then take 1 from each pair a complement. And here these a and a complement, these are really size, each of them has size n over 2. Okay? Well, how many does this get? If I take 1 from each of them, I don't mean how many ways are there to do it. How many sets I get? Well, I get half of all of the possibilities. So I get 1/2 of n choose k. Because there are n choose k different sets, and they all pair up in complements. Okay, the next question is, let's look at all three of these bounds. It would be a little bit annoying if the theorem that we have to prove next has 3 different bounds in it. The fortunate thing is that there are only 2 bounds, really. And already you see there are a bunch of constructions, so we won't go and categorize all the correct constructions, but if you're curious, actually that can be a fun thing to do. To be honest, it's actually worthwhile to do. You can go characterize the constructions, and for example, when n is bigger than, when you're when the first case is correct, when somehow the k is small enough, k smaller than n over 2, then in fact it turns out that you can categorize them as you actually have to contain 1 element, which is nice. Except that what I've discovered is those kinds of proofs, when you do a lot of analysis of these cases, it makes the most sense to try to fight with it yourself rather than to watch somebody else's logic go through. In fact, I just fought with it myself and made my own logic. Okay, now let's look at this. I want to consolidate this into 2 inequalities, 2 bounds. So there's 3 things here, but look, if you're in the third situation, if k equals n over 2, very fortunately, half times n choose k is exactly n minus 1 choose k minus 1. So that's nice. I only have 2 bounds to worry about. In the third case, this is exactly equal to n minus 1 choose k minus 1. Why? This is one of these nice things. Whenever I have combinatorial, like binomial coefficients, just a nice observation. I'll just put it over here. How did I do that thing with the blue? Here's the observation. If you're doing n choose k, well, that's equal to n times n minus 1 times, there's like k of these, divided by k times k minus 1, and there's k of those. And so because there's like the same number on the top and on the bottom, this is exactly equal to n over k, where I take out the first one, and then n minus 1 choose k minus 1. There we go. It sort of ran off the edge of the board, but this is just showing how you do n choose k anyway. It's n times n minus 1 times all the way down with k things, and then the k times k minus 1 all the way down with k things. Just pick off the very first n over k, pick over just that front piece, n over k, and then the remainder that's left over is just times n minus 1 choose k minus 1. Very, very useful identity, and you just apply that identity straight. On this one, if I have n choose k, that will be n over k times this n minus 1 choose k minus 1. Fortunately, n over k is equal to 2. So it's just that this is showing that the bound consolidates. So that means we now are equipped to state the next theorem, and we'll prove the next theorem, and it'll all fit today, and that will finish this topic. So there's a theorem, the Erdős-Colorado theorem. And what Erdős-Colorado theorem says is that, in fact, the maximum size of the intersecting family depends on these parameters. It says if we have that k is bigger than n over 2, I'm going to write that as 2k. If 2k bigger than n, I'll flip that around, n less than 2k, the maximum size is equal to n choose k, and else, which is if n is bigger or equal to k, the maximum size is equal to n minus 1 choose k minus 1. There's nothing to prove in the first statement if n is less than 2k, because that's the most you could have anyway. So the first statement is obvious. No matter what, you're going to have all of the sets. No matter what, you can't have more than all the sets, and just take all the sets and it works. So let's focus on the second case, where n is bigger or equal to k, and we now need to show that the maximum size is this, n minus 1 choose k minus 1. Now for that, I'm going to also observe that it has a relationship to n choose k, and that's why I'm leaving this still on the board here. So over here, n minus 1 choose k minus 1, I can rewrite as a fraction of n choose k. So that, by the way, is equal to the fraction k over n times n choose k. I simply just used this equality backwards. So because n choose k is n over k times n minus 1 choose k minus 1. Okay. So now I want to show that if n is big enough, then the maximum size of intersecting family is only k over n times all of them. And that's a nice statement. It's a fraction. Once you have it stated as a fraction, this also suggests a way that you could try to prove it. Now we want to show that if I have an intersecting family, at most, I can have k over n fraction out of all of the sets. So now, for our part, it just suffices to show that if you're given an intersecting family, so given an intersecting family of sets of size k, the maximum is k over n fraction of all n choose k. And now there is a proof of this in the probabilistic method book, where it's stated as a probability and do a random thing, but you don't really need to think about it that way. There's a much easier way to, not much easier, they're equivalent. But whenever you're trying to show k over n fraction of them, we just have to think back to how we showed with normal, when I don't have a restriction on k, the way you said the maximum size of an intersecting family was half of the total, was we took all of the different sets that we could have, and we paired them up, and we showed that one out of every pair can be in. If I want this fraction k over n, I should somehow I should take all of my sets that I might ever make, all of my sets of size k that I might ever make, and kind of group them together. Okay? Oh, actually, now the way I'm thinking about this is maybe the probabilistic will be easier. So let me take that back. We'll go with the probabilistic after all, because I will not really be grouping. I'll actually be multi-counting certain ones. Okay? But I will want to do something which can kind of pick out sets of size k in such a way that I somehow need to only pick at most k over n of them. I'm making a circle. The way you think of this is you actually think of writing your numbers 1 through n in a circle. Okay? So let me first state an idea, and then we'll see actually the probability is the easier way to think about this. But if I'm looking at all of these sets, here's one way to generate a set of size k. Can generate a set of size k like this. What you do is you write the numbers from 1 to n in a circle, randomly. You take a random circular permutation of the numbers from 1 to n. And it will look like something like 1, 2, 7, 5, 3, 4, n. Okay? And I didn't write all the numbers here, but it's just some random permutation. If I have this random permutation, can anyone suggest how you might use this random permutation to pick a k-element set? I want to show this is a very natural idea once you think of a random circular permutation. How might I pick a random k-element set then from this? I must use that there's a nice circle. I just need a procedure. So step 1 of the procedure, make this circle. Philip.
Take a random point and take the k elements around.
Yep. Take a random point, go this way, and take k elements. Next k. So the important thing, by the way, is that this is a way of generating a random set of size k. In fact, it's a uniformly random set of size k. If I use this procedure, what spits out at the other end will be with by symmetry as likely to be any set of size k as any other set of size k. So now I just need to show that this procedure, the probability that it spits out a set in my intersecting family, I need to show that probability is at most k over n. So it suffices to show that the probability this makes a set of size equal to k, not set equal to k, a set in the family, makes a set in the family, I need to show it's less than or equal to k over n. Well, if I want to now say the way the protocol works is first make a random cycle, and then choose a starting point randomly, uniformly at random, and go forward by k, if I want to show this big complicated procedure has probability of spitting out a set in the family of at most some size, it's also enough to show that no matter what circle I started with, given that circle, the conditional probability of making a set in the family is at most k over n. And why is that true? So that's actually the end of the proof. Why is it true that once the cycle is fixed, but once the cycle is fixed, the conditional probability of being in the family is it's less than or equal to k over n. That's all I need. And do you know why? Why is it at most k over n? If I have this cycle and it's stuck here, how do I know that my chance of getting something in the family is at most k over n? Aditya.
That's the probability of intersecting with that set.
You could say that. That's the intersecting of. You could say it's the probability of intersecting with this set. I think the way I want to say it is, I've got this thing. I've got this cycle. What's the most number of those things I can put down to intersect with each other? Because if I look at this circle and I now let me mark down which of those sets are in my family. Critically, my k is less than or equal to 2n. My k is less than or equal to 2n. And therefore, in the worst case, I mean not worst case, but the most I could ever put in is something like this. Does that make sense? Because this needs to be an intersecting family itself. And they are now forced to be intervals. Right? The main point is that at the beginning, these are just subsets of 1, 2, 3 up to n. Now we're saying we are looking at subsets of circular intervals. And if I go and draw which are the circular intervals that are in my family, that needs to look like an intersecting family of intervals. And the most number of intersecting family of intervals is obviously, they're all intervals, right? So if they're all intervals, you have no other choice than to go around like that. So what I'll say here is since at most k intervals in the intersecting family from this circle. Does that make sense? It's like once you stuck one of these down, the moment you stick down one of these, well, actually, you can already see what happens. If I have an intersecting family of intervals, they actually just have to be, from somewhere all the way along to somewhere else, and it's sort of like it starts here and it goes to there. Did that make sense to people? Like that's the most you can do with intervals. It starts here and then it goes, and to here. And the most you could have if you just look at it is at most k. And that's it. So that's actually the beautiful proof here. And in fact, the probability is useful. Originally, I was thinking maybe I can just have grouped up the sets. But in reality, the probability comes in handy because this 1, 2, 7, it appears once in this particular cycle, but it also appears in the cycle that goes 1, 7, 2. So the same set appears many, many times. It's not quite as clean as just saying, I took all of my n choose k sets and I grouped them into some groups. This lets you do some kind of repeat counting. Okay, so that's Erdős-Corrado theorem. Does anyone have any questions? Because that just finished the next topic cleanly. If not, then I guess that's it. That's it for class. I'll see you guys next time. Oh, Philip has a question.
A little bit off topic, but back with the intersecting sets. This feels slightly filtery. Is there any way to make a connection there?
It feels like filtery? What do you mean by filtery?
Like filters from set theory. Like you have a set which is closed upwards, and a family of sets which is closed upwards. Intersections are contained in the family.
Ah, okay. So, like, if it's a bunch of sets closed upwards with intersections in the family, yeah, I think these are all kind of related. I don't know off the top of my head how this could be used in one in that way or the other way. But the reason why extremal set theory is so important is exactly because these kinds of concepts appear a lot. So it may, if you know more about logic and more about set theory, something like this could be useful. Similarly to how something like this with these sets was useful for the Littlewood-Offord problem when we were taking random sums. And also we just saw that these kind of set things were also useful in that saturation number. I myself don't know enough about ultrafilters or filters to be able to properly answer that question. Other questions? Well, if no other questions, then I guess I'll see you on Friday. See you guys.